So now we need to do what we saw in the slideshow. We need to look at each individual joint. I think this might have been, I don't know, whatever. This is just an example from the slideshow. So we want to know like how much force is in AB. So that would be whatever these arrows are. If AB is pulling on joint A, then joint A is pulling back on AB with the exact same force, Newton's third law. It's also pulling back on joint B with the same force. So that would give us how much tension or perhaps compression there is in each joint. Now you may notice if you open this up that when I open it up on my computer, my personal computer, this example box was just like covering up all this, and that was just one of many frustrating things today. It says on the next page, redraw a free body diagram for the entire truss system, just like you did on page 2, but this time only lightly, so that you can replace members with their internal forces, like the PowerPoint example below. Make sure to include your calculated support reactions from step 3. Oh my gosh, how did you let me get away without writing that? So let's see if I can draw this lightly. So we're basically just recreating this drawing, but we're just gonna like draw it lightly. And so we can just come in here and draw arrows. So I'll give you a second, give me a second to get a pencil. Well, I just discovered that I can't really write lightly in pencil. Anywho, you see I drew it up, so pause the video if you need to sketch that out. And then, again, I would use pencil if I were you. Go back in there and draw all those things that we figured out. So this is joint A over here. This is B up here. This is why I wanted to leave you space here. Oh, that's not B. For mistakes, too. This was, I've already forgotten, 100 pounds. This over here was joint E. This is joint D. And this is C over here. We knew that RCY here was 110 pounds, I believe. We knew that RAX was acting this way, and that was 200 pounds. We got a sharp pencil. We had RAY over here, not to scale, 10 pounds. And then we basically, it's got some notes here on how to do this. But, you know what, I should do this in pencil. That stuff we know. So I'm going to come in here and I'm going to draw, this is AD, remember AD. We assume everything, let's just read this quick. No, never mind. Wow, it doesn't really tell us much, does it? Just remember our steps say draw everything in tension. That means coming out from the joints. If the members are pulling on the joints and the joints are pulling on the members, you know, the members that we care about. Oh my goodness, apparently I don't know my letters. This is AB, so it's pulling here. It's also pulling here the same amount. Member BC is pulling on joints B and C. This is CE, do them alphabetically. Assume everything's in tension. This is BE. And then we've got this force here called DE. And that's kind of a big step. But now what we have, assuming I haven't missed anything, are a bunch of individual free body diagrams that we can solve one at a time. And yes, it's a pain, especially when you have 5. I don't think, well, I'm pretty sure that 217 is a little bit easier, but you need to be able to do that even more on your own than this. So basically you got to look at it and say, which joint can I actually solve? I know very little about joint B. I know that there's 100 pulling down, so these two combined need to somehow pull up with 100, and all the lefts have to equal all the rights. But I can't really solve much there, really anything. Same with E. This doesn't even look right. We can tell that something's wrong with D and E because there's no up forces on either one of them. So something must be wrong there, but we'll worry about that later. What we can do is, since we know some forces here, we can see that we've got a left, we've got a couple rights, We got a down, we got an up, so we know that AD has to be in tension, has to be pulling up to the right, because something needs to counterbalance RAY. So, draw the free body diagram for joint A has been started for you. Make sure to include all known and unknown angles and forces, including X and Y vector components. I'll show you what that means in a second. Normally, you'd want to analyze all the mini free body diagrams above. I just talked about that. A is viable options. See next note. It's not the only one that's solvable right now. Again, these free body diagrams are usually not scaled unless you really want to get picky, which I am not going to, because that would be a waste of my time. What direction should member forces AB and ADB? ADB? We assume tension outward unless it's obviously not. For example, reaction force RAY down tells us something about AD. It's got to be part of it. Its vertical component's got to be up. Because up must equal down. AB is a little tougher. It could be left, could be right, because we have something to the right, something to the left. Whichever one is bigger is going to have to be counteracted. Whichever one's smaller are going to have the help of AB to counteract it. So it could be pushing into the joint, which means the the member itself is in compression. It's being pushed by the joint. It's pushing on the joint. Newton's third law. Let's see, AB is a little tougher, but you can probably tell how big ADX is. That's this guy. And how it compares to RAX. And see that assuming tension is safe. We'll find that out. Add the 4 arrowheads where they should be and correct both joints A and D above if necessary. You will need to do this whenever a force comes out negative. So if AB was actually pushing this way, that means it's also going to be pushing in on B. But we'll worry about it when they get to that. So I'm going to, what was this? This, remember, was, well, I don't remember, 56.31, which makes this 33. You could also label this guy up here, but we're getting kind of crowded here. So we're assuming, and I'm not even showing you any of that, not that it's new. RAX, what was that equal to? 10 pounds? That's not right. This was 10 pounds. RAX, I'm using a pencil now. 200 pounds, not to scale. Okay, so that means that, well, what you might look at right away is how big this guy must be. But since RAY is pulling down, ADY must be pulling up, which means that AD is acting this way, and you got to be careful with your arrowheads here. So that's 3 arrowheads. Now, we're going to assume if this is 10 pounds to counteract that, which is what we figure out later with our up equals down equation. If this is 10 pounds, this has to be smaller than 10 pounds, because at least those guys are to scale. So if you got 200 to the left and less than 10 to the right, you're pretty sure that this one's going to act to the right. But if you didn't want to think about it that much, you wouldn't have to. If you draw it the wrong direction, it'll come out negative. So flipping it, there's going to be some flipping involved here. Why did I staple this? Right horizontal and vertical equilibrium equations. Left equals right. So what are our left forces? REX. 2, I'm just going to skip and go right to 200 pounds equals our rights. We'll break down the trig next. But we got ADX, we're pretty sure is to the right, and AB, which we're decently sure is to the right. So we get ADX plus AB. Up equals down. What do we got? We already know this. We got ADY acting up because we know RAY from the previous deck is acting down. So ADY equals 10 pounds. Okay. Now we're going to break and do a little SOHCAHTOA. What is actually ADX equal to in terms of AD and SOHCAHTOA? So ADX. So if we use the 3369, ADX is on the opposite side. So the sine of 3369 is ADX over AD, opposite over hypotenuse. Flip that around, ADX is going to be equal AD times the sine 33.69. And then ADY, just to double check, is right here. It's adjacent to 33.69 degrees. So adjacent means cosine. AD times the cosine of 33.69 degrees. So we don't know AD, so we can't solve that. Can't solve either of these. Okay? What it says to do here is combine the last two steps, inserting known forces and angles, and solve for AB and AD. Here's where I definitely recommend, I should have done it more often, but I definitely recommend that you pause the video and go and try to solve for these on your own. Just look at what information we have here and what can we solve for. Pause for effect. Okay, so start with AD, after figuring out ADY from the vertical equilibrium. So basically we have ADY is equal to 10 pounds, and we also know that ADY is equal to AD times the cosine of 33.69. So we can just write ADY equals 10 pounds equals AD times the cosine of 33.69. From that, we can get that AD, doing some basic algebra, equals, figure it out, 12.02 pounds. Why did I write that there? Does that make sense? Again, this is 10, so that being 12, looks like 12 to me. Okay, now what can we do? Again, here, if you haven't already solved for AB, you should be able to figure out how to do it now just using our equations that we wrote up here. But pause it if you need to go and solve for that. So we got 200 pounds. I'm just rewriting this equation from up here. 200 pounds. Well, you know what I should do first? I should have done it down here. What is ADX equal to? Well, you know what? I'll do it next. 200 pounds equals AD, what's ADX? ADX is AD times the sine of 33.69. Okay, and that's plus AB. Okay, plug in this right here, do some basic algebra, and what do you get? We should get 193.3 pounds. It says box that up. Easier to pick out the answers when they're boxed up. Remember, if your answer comes out negative, you drew them backwards. We avoided that here by changing the direction of AD before we started calculating. Update the free body diagram for A in steps A and B with the newly calculated forces. Only 4 more joints to go. Fake excitement. So, come back here. This is 193. You could write it over here, or you could just write it under there. I'm going to write it both places. 193.3 pounds. Pencil's not as sharp as it used to be. And then AD, what am I doing, like 4 digits just for the heck of it? Try not to round too much. This was, whoa. This was 12, oh my goodness, 12.02 pounds. 12.02 pounds. So AD is pulling on both joints A and B with 12.02 pounds. That means that the joints themselves are pulling outward on AD with 12.02 pounds. So AD is in tension. And so is AB. Nothing came out negative because we had this there. PLTW would like you to just leave everything drawn wrong and everything to come out negative. If we were taking the test, you would say RAY is negative 10, not 10 downward, because that's not how they do things. And their way is foolproof, but also more confusing. So now we have to move on to the next step, figure out what to do next. So you could look at your joints here while you're getting the next video loaded and say, what can I solve for now? Might be more than one thing.